All right, everybody, welcome to Math with Grace. Today we're going to be going through Pre-Calculus, Unit 2, Section 4. Section 4 begins on page 53, and it's entitled Complex Numbers. And so we're going to be talking about an introduction to complex numbers. And it says, complex numbers are numbers that are a combination of real and imaginary. Okay? We're going to go through some review of real numbers. Okay? The counting numbers are called natural numbers. Whole numbers are described as a set of numbers which includes 0 and all of the counting numbers. Integers are used to represent negative values, and so they include all of the whole numbers as well as their opposites. All right, let's turn the page. Looking at the top of page 54, it says rational numbers are used to describe partial or fractional amounts, which includes every number that can be represented as the ratio or fraction of two integers. So therefore, all integers, and thus all natural and whole numbers, are rational numbers. Numbers that cannot be represented as a ratio of two integers also occur in real life, it says, and they're called irrational numbers. They're numbers that whose decimal values go on and on without a repetition or a pattern. A common one that we use quite a bit is pi, right? It says this system of numbers is known as the real number system. Okay, those are all real numbers. Even irrational numbers are considered real numbers, okay? But there are also imaginary numbers. We use the letter I to denote the square root of a -1. I stands for imaginary. So if we had the square root of 16 normally in a real number situation, we would not be able to solve this. But because the square root of -1 is I, we can separate the -1, the square root of -1 from the square root of 16, and then solve. The square root of 16 is 4. The square root of -1 is I. All right, and we can use that quite a bit with solving using the quadratic formula. We can solve as long as we pull out or separate that square root of -1, we get I. Okay, and that is an imaginary number. Now it says here at the top of page 54, the second column, complex numbers have both a real number part and an imaginary part. Okay, for that example that they showed right down there, -3/2 was the real part, and plus or minus the square root of 11 over 2i is the imaginary part. So complex numbers can be written as z equals a plus bi, where a is the real part and b is the imaginary part. And therefore, just like we have the Cartesian plane, we also have a complex plane. And the complex plane, the x-axis is now called the real axis, and the y-axis is called the imaginary axis. So we can graph these things. All right. Another way of graphing complex numbers is in polar form. Okay. Polar form is written as z is equal to r times the quantity cosine theta plus I times the sine of theta. And it seems like a lot, but let's just break it down. It says here that r is the length of the vector between the origin and the point. So r is the length of this, okay? And then it's for a given value of r, the points must lie on a specific circle in a complete complex plane. And so at the top of page 55, we can see what a complex plane or a polar plane looks like. Right? It can make a circle. Usually it makes a angle. Sometimes it goes around more than once. And so the angle is pretty long. Okay. Theta, that's this 0 with a line through it, the middle, is the angle that the vertex makes with the real axis. This is theta. Okay. Every point on the complex plane can be described with these two values, r and theta. And so here at the bottom of page 55, we'll look at the polar form again. So it's essential to be able to convert between polar and rectangular. This was rectangular up here, right? Z equals AB, or A plus BI. That's rectangular. This is polar. So to be able to go back, if you're starting with the polar form, R times the quantity, cosine theta plus I sine theta, all you have to do is distribute to find the rectangular form, which means distributing this R, right? So you get Z equals R cosine theta plus IR sine theta, where A, remember our Z equals A plus B up here, A equals R cosine of theta, and B equals R sine of theta. That's the imaginary part, okay? So let's just take a look at an example and see what the heck is going on here. They want us to convert Z equals 8 times a quantity cosine 225 degrees plus I times a sine 225 degrees to rectangular form. Now, you could use a calculator to find the cosine and the sine of 225 degrees. They also have this wonderful little diagram here, which is very useful, and I would suggest photocopying and keeping a little bit with you as you go forward here to do the work that you can reference, or at least maybe fold the page over so it's easy for you to find again. Because if we look here and find 225 degrees, we see that the sine is negative square root of 2, and the cosine is negative square root of 2 over 2. Okay, so you should find that the cosine of 225 is negative 2 over 2, and the sine is negative square root of 2 over 2 as well. So if we put that now into this equation, right, and then distribute our 8, so we're going to have 8 times the cosine of theta, right, which we can reduce our 2's. It becomes negative 4 times the square root of 2. And we have 8 times the sine of theta, which is negative 4 over 2. We can rewrite this as negative 4 times the square root of 2 minus 4i, because we don't want to forget our I. Remember, it is part of the formula, times the square root of 2. Okay? And then it says here, it can also be helpful to go back the other way, right? To go from rectangular to polar form, but it requires a little bit more complicated equations, right? So rectangular form, remember, is Z equals A plus BI. Thus, R equals the square root of A squared plus B squared. Remember, this is the R. And if we consider this a right triangle, right? This here is A and this is B. So R is equal to A squared plus B squared. Well, the square root, right? R squared, it's the Pythagorean theorem, right? R squared is equal to A squared plus B squared. So R must be equal to the square root of those two things added together, right? And then it says here that you also know that the tangent of an angle is the opposite over the adjacent. So here's our angle. This is what we're looking for, right? The tangent is opposite over adjacent. So B over A. So to find the tangent, right, we're taking the tangent inverse, or however we say that part, and we're solving for the tangent using this fraction or that decimal value. Okay, let's turn the page and finish this problem. All right, we're looking at the example at the top of page 56. Convert the complex number Z equals square root of 3 plus I from rectangular form to polar form. Remember that the real number, I guess I can make that a number sign. The real number is A, and the imaginary is b. Okay? So this is a, and this is my b. So when we take a squared plus b squared, it's the square root of 3, the quantity squared, plus 1, because this is just 1i. So we get the square root of 4, or 2. And then to figure out our theta, we take the inverse tangent of b over a. So now we have 1 over the square root of 3. But, and you might be wondering how they got from here to here. Remember, we can't have a square root of 3 in the denominator. So if we have 1 over the square root of 3, we need to get rid of the square root of 3 in the denominator by multiplying the whole thing by the square root of 3 over the square root of 3. Right? And so this becomes the square root of 3 over 3, which is what we have here. So that's the tangent we're looking for. Okay? We put it in your calculator, square root of 3 divided by 3, inverse tangent, and it will tell you that that's 30 degrees. And so now you can write it in polar form. We know the r is 2. So it's 2 times the quantity, cosine 30 plus I sine of 30. All right, so not a lot more math, but it definitely is more math. Okay, let's take a look at a couple of these problems together. Let's look down here at number 4. It says a complex number is graphed on the complex plane. Write this number in rectangular form. So we want our real number, remember, z equals a b plus bi, right? So the real number is on the real axis, and that is at 2. My imaginary number is at -4, so that's going to be plus -4i. I like to make my eyes big. So there we go. 2 minus, basically, 4i, which is letter C. All right, so don't forget the form. Let's take a look at the top of page 57. A complex number is graphed on the complex plane. Write the number in polar form. So remember, our polar form is equal to r times the cosine of theta plus I times the sine of theta, okay? We know r is 4, and theta equals 60 degrees. So this would be written as z equals 4 times the quantity cosine 60 degrees plus I times the sine of 60 degrees. All right, easy enough. Gave us a lot of space for that. Let's take a look at the next one, number 6. Convert the number z equals 32 times the quantity cosine pi over 3 plus I times the sine pi over 3 into rectangular form. The a, remember, is going to equal these two things multiplied by each other. So 32 times the cosine of pi over 3. Looking on that chart just before this, that's 1/2. And then b is going to equal 32 times the sine of 1/3. Square root of 3 over 2. Okay, so if you look back at that chart on the page before, it has the set of parentheses, right? We have cosine, comma, sine, all right, in that chart. So half of 32 is 16, right? And same here, right? 2 goes into 2 once, 16. So this is equal to 16i times the square root of 3. And we are adding them together. So we have letter A. Okay, let's do another one of these. Convert the complex number 2 times the quantity cosine 210 plus I sine 210 into rectangular form. Again, my A is going to equal 2 times the cosine of 210 degrees, which is negative square root of 3 over 2. and my b is going to equal 2 times the sine of 210 degrees, which is a -1/2. Okay? So working out a, my 2's canceled, so I have negative times the square root of 3. And my 2's cancel here, and I get -2i. All right? So my answer is negative square root of 3 minus 2i. Oh, no, not 2i, minus I. Sorry, I canceled my 2's. I forgot. Okay, check your work. Negative square root of 3 minus I, which is here, letter D. All right? Let's convert 1 here to polar form, just like we did up here at the top of page 56. It says approximate all angle measures to the nearest degree. Fine. Okay, so we have z equals 3 plus 2i. Okay, so remember, my a is equal to 3, and my b is equal to 2i technically. So to find my r, I'm going to find the square root of 3 squared plus 2 squared, which is equal to the square root of 9 plus 4, or the square root of 13, right? I'm just going to leave it as a square root of 13. Square roots aren't inherently bad, right? To find my theta, I'm going to find the reverse tangent of b over a. So 2 over 3. Now, to do that, we're going to pull out our calculator. Okay. Let's see, turn it on. And we are going to take 2 divided by 3 and get blah, 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 blah. And then my reverse tangent or inverse tangent, I usually call it reverse, but inverse tangent is here. So shift tangent, answer, close my parentheses, equals. So it says 33.69 degrees, and so they want you to round to the nearest degree. So 34 degrees. So to write out the final answer is going to be z equals square root of 13 times the quantity cosine 34 degrees plus I times the sine of 34 degrees. Okay? Here we go. All right, go ahead and finish the couple we didn't do together, and then we'll meet here for the next part of section 4. The next part of section 4 begins on page 58, and it's titled Operations Using Complex Numbers. And when they say operations, they're just talking about adding and subtracting, multiplying and dividing, okay? So review your vocabulary, and then let's take a look here. Addition and subtraction, right? When adding complex numbers, you combine real numbers together and combine the imaginary numbers together. So adding -2 plus 4i and 3 plus 2i is the same as -2 plus 3 plus the quantity 4i plus 2i, or 1 plus 6i. Okay? Pretty basic adding. Okay, let's take a look up here at our example. It says addition and subtraction of complex numbers can also be determined graphically, right? Now, you can always just check your math the good old addition way, but it can be determined graphically. So, z sub 1 is equal to 3 plus 6i, and z sub 2 is equal to -4 plus 2i. So we start by plotting the first complex number on this complex plane, right? Where, remember, the x-axis is the real numbers and the y-axis are imaginary numbers. So each one of these, technically, it has an I next to it, right? So to graph it, we just go +3, +6, and there's my z sub 1, right? Now, to graphically add the z sub 2, I don't want to cut it off the screen, but we need to slide down here. Okay. You do the same thing the same process, except you start from z sub 1 instead of the origin point. So instead of going back here and plotting z sub 1, or z sub 2, sorry, you're going to start at z sub 1 and plot z sub 2, which is a -4, -2. So we're going to go 4 units back and 2 units down, okay, because they're both negative. And so this is our point, which they're calling z sub 3, because technically it's a new point. But they want, and then they graphed as well, just regular z2 by itself. And they want you to see that the slopes are the same. The slope of this is the same as the slope of this, because we added this number, and we got this one, okay? So what is z3? Well, it's -1 plus positive 4i, right here. Now, you could have easily have just 3 minus 4 is -1, 6 minus 2 is 4i. You could have done it that way, but this is how they want you to do it graphically, okay? So look at the next column. To find the difference between two complex numbers or vectors, you follow the same process we just did, except that you change direction for the second part because you're subtracting it, okay? So the same two numbers, 3 plus 6i and -4 minus 2i, you plot your 3, 6i, right? And now because we are subtracting it, which is going to be -4 and -2, we're going to the right 4 and up 2. And so that is this is our new addition of the two, which is at +7 plus 8i here, okay? So you can add them, subtract them mathematically. You can also do it on a graph. All right, let's turn the page. Top of page 60 says polar form of a complex number. It says to change from z equals a bi to polar form r times a quantity cosine theta plus I sine theta, you can use the following, right? We did that a minute ago on the other page. So they want you to convert the number 1.73 plus I to from rectangular, to polar form. So they found that the r is 2 and the theta is 30 degrees. Okay, 2 times the quantity cosine 30 plus I sine of 30, right? We've done those over there. I feel like this maybe is a mistake and probably shouldn't be in this part, but that's okay, because now we're going to go back to talking about operations such as multiplication and division. Multiplying complex numbers in rectangular form is similar to the process you use multiplying polynomials, right? For example, 3 plus 9i, the quantity, times the quantity 5 plus 4i equals 3 times 5 plus 3 times 5 plus 3 times 4i plus 9 times 5 plus 9i times 4i, right? And then you have to reduce, combine your like terms, blah, 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 okay? But see here that we ended up with a I squared, and it says, notice that since we define I as the square root of 1, I squared, because the square root of -1 squared is -1. So I squared is equal to -1, and so on and so forth on down the line of i's, however high they're going to go in this book. So there we have multiplication. It says, something interesting happens, however, when you multiply complex numbers in polar form. So here are the two complex numbers in polar form, and they go through this multiplication, and then we're just going to follow along a little bit. But up here at the top of page 60, second column, it says you're going to use trigonometric identities and simplify. Now, the identities we've not really gone through in these books so far, so we're just going to take their word for it, okay? And we get that z sub 1 times z sub 2 is equal to r sub 1 times r sub 2 times the quantity cosine of theta 1 plus theta 2 and I sine of theta 1 plus theta 2. In other words, it says all you have to do is multiply the vector lengths and add the angles. So let's take a look at what that means. In this example, represent the product of AB graphically, given that A is equal to 2 times the quantity cosine 30 plus I sine 30, and B is equal to 3 times the quantity cosine 45 plus I sine 45, okay? Well, that is a chunk of stuff, right? But it said here, all we have to do is multiply the vector and add the angles, okay? So we know that the product of A and B will have a radius that is the product of their radii. So 2 times 3, so 6, right? And the angle will be the sum of their angles. So 30 and 45 is 75 degrees. Thus, AB has a polar coordinate of 6, 75 degrees. Remember, polar is this weird swirly thing. Circular graph. I will check ahead if we need, I actually have this or can make photocopies of a graph like this. So if we need it up ahead, I'll make sure we have it available to us. But that's it. That's all we had to do. We multiplied the two r's together. We added the thetas. We got 6, 75. All right? Okay. Up here at the top of page 61, it says division is the inverse of multiplication. So to divide complex numbers, you perform the opposite operation as you did to multiply them. You divide the vector lengths and subtract the angle measurements. It says here as well, if you are given two numbers to multiply in rectangular form, you may want to convert them to polar form before you perform the multiplication. I'm not really sure why, because multiplying in rectangular form wasn't that complicated, although definitely polar form is definitely easier because you're just multiplying and adding, right? Or multiplying or dividing and subtracting if you're doing division. I don't know. I guess it's up to you, right? The answer should be the same. So let's take a look at some of these problems. Let's look at number 411. Yeah. Use a geometric representation. So I know it's real hard to see even if you have the book, but there's definitely a graph right here. Use a geometric representation to determine the sum of the complex numbers. A equals -2 minus 6i. B equals 5 plus 9i. All right, I took a second and set up my graph here. We are talking about sums, so remember a sum is adding. We are starting at A, which is at -2, -6. So 1, 2, 2, 3, 4, 5, 6. So down here. And we are adding, so this is my A. We are adding 5 plus 9i. Okay, so we're going to the right 5 and up 9. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. And this is my B. Well, technically this is what, Z3. B would be somewhere else, but we've added the two things. So it's going to look like this. And so what is our Z3? Where are we on our coordinate plane? We're at 1, 2, 3, so +3, and 1, 2, 3, so +3i, right? So we're at 3. Oh, see, they try to get you. We're at A, point A. All right, let's do another one, number 12 here. Let me set up my graph real quick. All right, so here it says use geometric representation to determine the difference, which is now a subtraction, of the complex numbers. We're starting here. Oh, it's the same points, right? So we're still starting at -2, -6. So 1, 2, oh, 1, 2, 3, 4, 5, 6. I did not leave myself enough space to subtract these. I should have read the problem first. Because now we're subtracting, we need to go the opposite way, which means I'm going to the left 5 and down 9 points, right? So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, I don't know, 6, 7, 8, 9, we'll say over here somewhere, right? Now it's off my graph. Note to you, move your x-axis up, or your real number axis up a little bit higher. I probably should have read it first before I set up my chart, but hey, we are where we're at, right? So let's just take a look at it numerically to make sure we get the right numbers here. We have -2 minus 6i, and we're subtracting 5 plus 9i. Okay, so -2 minus 5 is a -7, which we could have figured that one out pretty easily. And -6 minus 9 is a -15i. So -7 minus 15i is letter C, and that's where our difference ends up. Okay, that is the difference between those two problems. All right, let's turn the page and do a couple more. Problem number 13 here on page 62, it says complete the indicated operations with the complex number a equals the square root of 3 minus I, and b equals -I. Okay, well, all right, a plus b is going to be the square root of 3 minus 2i, right? We add the real numbers. That b doesn't have a real number, it's only imaginary. And we added the imaginary numbers. What about subtracting? Well, we're still going to have this square root of 3 because it doesn't have anything to add or subtract from. But then we have I minus I, so it's just the square root of 3. Okay? To multiply, now here's where it said you could change it to a polar form to multiply, but I'm just going to multiply it as it sits because it's just a monomial times a binomial, so not too challenging. And we end up with -I times the square root of 3 plus I squared. Now remember, I squared is equal to -1. So that needs to be reduced. If ever you have an I squared, it has to be reduced. So we have -I times the square root of 3 plus, or -1, sorry. And I'm writing them in the wrong order. But what's done is done. They should be written in the other order, since technically -1 is a real number and I is an imaginary number, right? So then division. We have square root of 3 minus I over -I. And to divide that, I don't see that it can be, that there's anything else to simplify it. So there we have it. I suppose you could multiply by I if we don't want an imaginary number in the denominator. Let me check and see if that's what they want you to do. Hold on one second. Yes, all right. So they do not want that I in the denominator. I love it when they don't tell us things. All right, so no I in the denominator. That's fine. And that's nothing we can't handle. To get rid of this I that's in the denominator, we're going to multiply the numerator and the denominator by I. Okay? And so here we're going to have I times the square root of 3 minus I squared over a -I squared. Okay? Remember, I squared is -1, so this becomes a +1, so our denominator is gone. And we end up with, this also becomes a -1, but there's a negative here, so it becomes a +1. So we have 1 plus I times the square root of 3. I wrote it in the correct order that time. All right? So there you have it. Let's take a look at number 14. For number 14, it says, which of the following is a correct representation of the product of z1 times z sub 2? Where z sub 1 is this and z sub 2 is this. Select all that apply, which makes it sound like there's more than one answer, but let's take a look. Remember, when we multiply these in polar form, we're going to multiply r sub 1 times r sub 2, and then we're going to add theta sub 1 plus theta sub 2. Okay? So, to do this, we have square root of 3 times the square root of 6, which is equal to the square root of 18, which can be reduced to 3 times the square root of 2. Adding our thetas, we have square root of 4, or sorry, pi over 4, and 3 pi over 4. Okay, so I have pi over 4 plus 3 pi over 4 is going to be equal to 4 pi over 4, which is equal to pi. Okay, so 3 times the square root of 2, comma, pi over 2, no, that's not correct. 3 times the square root of 2 over pi, E is definitely correct. And I don't see, it wouldn't be these unless they're rewriting it in polar form. Because then this would be correct. And I think there is one more answer here, because the cosine of pi is -1. So if we looked at this, because this is correct, if we looked at this and actually like distributed it, the sine of pi is 0. The cosine of pi is a -1, which you could look at that circle chart, remember a few pages back. And so that would mean that this is also correct, because if you multiplied it out, it would just be square root of 3 times square root of 2 times a -1. Okay, so this has 3 answers. Select all that apply. I guess they're just making sure you write it in multiple forms and checking that everything simplifies. Okay, let's do one more of these together, which is number 15. It says, which of the following is the correct representation of the quotient of z sub 1 divided by z sub 2? Where, here we go, select all that apply again. So we got to make sure we're going through this all the way. So remember, we're going to have r sub 1 divided by r sub 2, and theta sub 1 minus theta sub 2. Okay, so we have 8 divided by 4, which is equal to 2. And we have 3 pi over 2 minus pi over 4. All right. Now, to get these to actually work out, just like any other fraction, they have to have a common denominator. So I'm going to have to multiply this one by 2. So I get 6 pi over 4 minus pi over 4 is equal to 5 pi over 4. Okay, so I have 2 and 5 pi over 4, so definitely E, right? If we were to rewrite that out, it would be D, right? 2 times the quantity cosine pi over 5 pi over 4 plus I sine pi over 4. So definitely D. But now let's go and look at that chart again and see what pi over 4 is. So 5 pi over 4 was that 225 degrees, right? Which was represented by negative square root of 2 over 2, comma, negative square root of 2 over 2, okay? So if we put that into here, we've got 2 times the cosine of, or not cosine of, 2 times square root of 2 over 2, negative square root of 2 over 2, because I'm distributing, right? Plus 2 times this negative square root of 2 over 2. The 2's are all canceling here, so I end up with negative square root of 2 minus the square root of 2, which is equal to negative 2 times the square root of 2. Oh, no, because this is an I. See, I almost missed it because I take it out and I forgot to put it back in. So it's negative square root of 2 minus I times the square root of 2. Okay, B. Phew. All right. That's quite a bit of math. That polar chart on, what page is this on? Page 55 is going to be quite useful in doing these problems. So either mark it or make a photocopy and keep it with you, whatever works best for you. All right, go ahead and finish the rest of these and then meet me back here for the next part of section 4. All right, page 63 is titled Conjugates and Polynomial Identities. Read over these couple of vocabulary reviews and let's take a look at these, what we are going to learn here, starting with conjugates and division. This says the conjugate of a given complex number is a complex number with the same real part, but the opposite of the imaginary part. So if you have a complex number, a plus bi, the conjugate of that would be a minus bi. Okay? If you multiply a complex number by its conjugate, you simply take the sum of the real component and the sum of the imaginary component squared. It becomes a sum and difference binomial. So we take the first one squared, second one squared, and that's our answer. Okay? So here's, it says we use conjugates when we find the quotient of complex numbers. When we have a fraction, remember, we can't have an I in the denominator, so we have to multiply this fraction by its conjugate. In this case, negative 9 plus 5i. Okay? That is its conjugate. No, sorry, negative 9 minus 5i. I got to work on my i's here. Negative 9 minus 5i is the conjugate here. So you multiply the numerator and the denominator by that, and that happens here is it cancels out the I that's in the denominator. And then we reduce and find our answer. Okay? Let's turn the page. Top of page 64 says the modulus is the distance from the origin to a complex number on the complex plane. And it's written like this, square root of a squared plus b squared, right? So finding the modulus of 3 minus 4i is simply taking the square root of 3 squared plus the quantity negative 4 squared. And you get, for this particular one, you get 5. Okay, so the modulus is a pretty simple part. Here are some polynomial identities that we're going to review. Okay. And it says, recall that a complex number is made up of real and imaginary parts. So when we add, this is just review of all the things we just did, right? We add the real, we add the complex, or the imaginary. When we subtract the real, we subtract the imaginary. When we multiply through the FOIL method, right, we have to reduce. Okay, here's an example. This was all review of what we've done earlier this lesson. It says, find the roots of the following equation. X squared plus 49 equals 0. What you know about complex numbers and the sum of two squares, you can factor the left side of the equation. Okay? X, because it's a plus, right? This is not something that we would normally be able to factor. But because it's a plus, we can factor it like this. X plus 7i times the quantity x minus 7i, okay? And then it would end up being, if we multiply that out, right, how you're wondering, well, I got a plus times a minus, how is that going to give me a plus? Well, it's going to give you a technically a negative 49i squared. And what's I squared equal to? Remember, it equals a negative 1. So that's how we get the positive 49. Okay, so when we're splitting something like this, it's going to be split into a sum and difference binomial still, but we have an I there this time. We set them equal to 0, so x is equal to negative 7i or positive 7i. Okay? Second column, page 64, top of the page. It says some other useful polynomial identities are the cube identities. So remember, when we have a plus cube, there's a plus here, but the minus there. Okay, and when we have a minus cube, we have a minus here, and they're all pluses. Right? This probably haven't seen it in a long time, but we've talked about these types of things in the past. So finding all the roots of this equation, because we're talking about a cube now. So our x and our b are what we need to go into this equation, right? X to the third equals 64. Actually, we didn't even need that part right now. We will later, though. So x to the third equals 64. The cubed root of 64 is 4, right? So that's the real number solution. But it's not enough for us to actually finish this equation because that's one root, and we should have 3 roots, right? So now we have to use the difference of cubes to factor the left side of the equation. Because technically, since it's 4, right, this is x cubed, minus 4 cubed, right? That's my a and my b, or my x and my b. So here's how they write it. X minus 4, right, we're on this one, times the quantity x squared plus bx, or 4x, plus b squared, which is 4 squared, which is 16. Okay, now we can't factor x squared plus 4x plus 16 because it doesn't work, but we can use a quadratic formula, and we come down here with our imaginary numbers, and now we actually have 3 roots. We have 4, and then we have negative 2 plus 2i square root of 3, and 2, it should be negative 2, minus 2i square root of 3. Okay? So that's how we get all of our roots from that type of problem. Okay, let's look at some of these. These last couple sections of this section are quick. 419. Find the quotient using the conjugate of the denominator. Show your work. Well, remember, the conjugate is the same real and the opposite imaginary. So 6 plus I is my conjugate. All right. I'm just going to FOIL out the numerator. So 4 times 6 is 24. 4 times I is 4i. 2i times 6 is 12i. And 2i times I is a positive 2i squared all over 6 squared, okay, and negative I times I, which is a negative I squared, right? Combining our like terms and reducing our I squareds, okay, remember, we can reduce these. So 24, combining my i's, is 16i. 2 times negative 1 is a negative 2, all over 36 minus 1, right? And this becomes a plus. So in the numerator, we have 22 plus 16i all over 37. And 37, I'm pretty sure, is a prime number, so we're not going to be reducing anything. So there's our answer, okay? For number 20, it says find the modulus of the complex number z equals negative 2 minus 6i. Now remember, this negative 2 is my a, and this negative 6 is my b. So you take the square root of negative 2 squared plus negative 6 squared, or the square root of 4 plus 36, which is the square root of 40. That's 4 times 10, so it's going to be 2 times the square root of 10. Okay, positive, and so we have A. All right. They want us here to find all the solutions, number 21, for x to the third minus 8 equals 0. Well, we're going to move the 8 to the other side, so x to the third equals 8. The cubed root is how we solve that, right? The opposite of cubing something is taking the cubed root. So x is going to be equal to 2, right? Because the cubed root of 8 is 2. Now that's great and all, but that's not all of our solutions. So now we have the x and we have the b. We are adding these two. Sorry, we're subtracting. So this is x minus 2, right? Because if we moved it back over, it would be negative 2. So using our formula up here, I don't know if you can still see it. Using our formula up here, we have x minus b, or x minus 2, times a quantity x squared plus bx, so plus 2x, plus b squared, so plus 4. Is there a factor of 4 that adds up to be a 2? And there isn't, so we need to use quadratic formula. A equals 1, b equals 2, c equals 4. So we have negative b plus or minus the square root of b squared minus 4ac all over 2a, okay? So I have negative 2 plus or minus the square root of, this is 4, minus 16, so negative 12, all over 2. Now remember, this square root of negative 12 is the same as the square root of negative 1 times the square root of 12. That's how we get our I. That's how we pull our I out. So this is negative 2 plus or minus, we'll do the I part in a minute. The square root of 12 is 4 times 3, so we're going to have 2i times the square root of 3 all over 2. Since they all have a 2, if we factor the 2 out, then we get negative 1 plus or minus I times the square root of 3. And remember, this is two answers. I'm not going to write it separated, but here's one answer, and here are two more answers. So that is our 3 answers. Okay? All right. Finish these and meet me for the, I believe, the final section of this. Yeah, final section of this section. Final part of this section. All right, the final part of section 4 begins on page 66, and it's titled Distance and Midpoint. Review your vocabulary, but let's just jump in here. It says the distance, or computing the distance between two numbers in the complex plane, is essentially the same as calculating the distance between any pair of real number coordinates. Remember, here is our example, right? We take the square root of a sub 1 minus a sub 2, the quantity squared, plus b sub 1 minus b sub 2, the quantity squared. Same thing, same process. It's what we would do to find the distance in a regular Cartesian plane. That's what we're going to do here as well. So find the distance between two complex numbers. Z sub 1 equals negative 5 plus 2i, and z sub 2 equals 3 plus 4i. Remember, the a is the real number, the b is the imaginary. Okay, so we're putting in the information, solving, and getting our answer. It says another way to think about the distance between two complex numbers is the modulus of their difference. Okay, looking at that. Find the distance between two complex numbers in this complex plane. Z equals negative 7 plus 8i, and z sub 2 equals 6 minus 2i. First they find the difference, and so here they have the difference, and then they find the module of the difference, or the modulus of the difference, using 13 for the A and 10 for the B, negative 13. And they get the distance is 200, square root of 269. Now, I don't know that that is worth the time any more than doing it this way. I mean, you should come up with the same answer, so I don't necessarily see the point because here you're taking an extra step, but we'll decide as we move forward through some of those points, right? But there's two ways to find the distance. Top of page 67 now, we're talking about the midpoint. It says finding the midpoint of two complex numbers is similar to finding the midpoint of two points on the Cartesian plane. You take the average of the real components and the average of the imaginary components, just like we would have normally in the other one. So z equals -5 plus 2i, z sub 1, z sub 2 equals 3 minus 4i. So we take the average of the real numbers, okay? And then we add the average of the imaginary numbers. And we get this answer, -1 comma I, or negative I, all right? Piece of cake. Okay, let us do some of these problems together, okay? Find the modulus of the complex number z equals 1 minus 2i. Remember, the modulus is just the square root of a squared plus b squared. Okay, so we have the square root of 1 squared plus -2 squared, which is the square root of 1 plus 4, or the square root of 5. And I forget, do we put the I there? I don't think we do. No, square root of 5 is the modulus for 23. So 24 says find the modulus of the complex number z equals 4 plus 3i. So we have the square root of 4 squared plus 3 squared is equal to the square root of 16 plus 9, which is the square root of 25, so that is equal to 5. All right, let's turn the page. For problem number 25 on the top of page 68, it says find the distance between the origin and the complex number z equals 6 minus 8i. Now they're using the word distance, but remember the definition of a modulus is the distance between the origin and a complex number. So again, we're just finding the square root of 6 squared plus -8 squared. So that's going to be equal to the square root of 36 plus 64, which is equal to the square root of 100, which is 10. Okay, so the distance is 10. All right, let's look at number 27. Find the difference between the complex numbers z sub 1 equals 5 minus 2i and z sub 2 equals 8 plus I. Use the modulus of that difference to find the distance between the complex, or between the numbers. Okay, so find the difference, then you find the modulus. So I'm going to take 5 minus 8 plus, I guess, -2i minus I. So that gives me -3 minus 3i. That's the difference. So now they want us to use the modulus to find the distance between the numbers. So that's the square root of -3 squared plus the square root of -3 squared. So the square root of 9 plus 9 equals the square root of 18, which is equal to 3 times the square root of 2. So letter D. All right. Find the midpoint between the complex numbers z sub 1 equals 6 minus 2i and z sub 2 equals 8 plus 4i. Okay, it's 6 plus 8 divided by 2 plus -2 plus 4 divided by 2. I, right? 6 and 8 is 14 divided by 2 is 7. -2 plus 4 is 2 over 2. So this is just plus I. That is the midpoint between those two things. So what do they usually call that? Z sub 3, right? All right. Okay. Go ahead and finish these. As always, if something comes up, if you have any questions, do not hesitate to contact me. Otherwise, until next time.